Okay, so in the real gases, what are things you are studying? First, I'll highlight all those things. Okay, in the real gas, we discussed mo mainly the van der Waals equation. Okay, the van der Waals equation is given by, you remember this formula, that is P plus A by V square into V minus B equals to RT. Okay, so where P is the pressure of gas, V is the specific volume, A and B are the constant values. Okay, as I said, in order to find out A and B values, you have to refer the thermodynamics data handbook. Okay, so the thermodynamics data handbook will be permitted for your internal examination as well as for your final examination. Okay, and for all the uh, gases, we are having the particular value of A and B. R is general gas constant. So we are having two types of gas constant. One is general gas constant and another one is the universal gas constant. The relationship between general gas constant and universal gas constant is given by R equals to R bar divided by M. Okay. So directly we'll go to the numerical problems on real gases. Okay. You see the numerical problem one. The specific volume of carbon dioxide gas at 100 degrees Celsius is 1 meter cube per kg. Okay. Use van der Waals equation, determine the pressure exerted by carbon dioxide gas. Compare the result by treating carbon dioxide gas as the perfect gas. Okay. So here you should have the idea of ideal gas also. We discussed the difference between the ideal gas and real gas. Okay. So in case of ideal gases, no intermolecular forces of attraction are taken into consideration. Okay, in case of real gases, the intermolecular force of attraction is taken into the consideration. Okay. So first, as I said, I shared uh, the three tables. Okay, one is to find out the gas constant R bar and the values of A and B. Okay, mainly van der Waals equation is used in the real gas. Okay, so from table C8. Okay, we're having table number C8, page number 59 of data handbook. Okay, so I'm giving the author name Nijaguna and Samaga. Okay, please remember thermodynamics data handbook by Nijaguna and Samaga. Okay, so suppose if you want to take that book, you can take it. I shared all the required pages in the Google Classroom and also in the WhatsApp. Okay, so using that value, you are going to find out the A and B. And you have to search what kind of gas is given in the problem. So here, carbon dioxide gas. Sometimes they can give nitrogen also. In that case, the value of A and B vary. Okay. For carbon dioxide gas, from the page number 59 of table C8, we'll get the values of A and B as 365.6 kilounits and B is 0.0428 kilounits. Okay. Now we have to find out the specific volume of the gas. Okay, so in terms of a meter cube, so it is 1 meter cube per kg, but you have to express in terms of meter cube per kg mole. In that case, we have to multiply the whatever specific volume is given, multiply by the molecular weight of carbon dioxide. Molecular weight of carbon dioxide is 44. How will get 44? Means C is 12 and O2 is 32. So we'll get carbon dioxide gas molecular weight as 44 meter cube per kg mole. See, unit is meter cube per kg mole. If it is meter cube per kg, then it is only one. Okay. So here you see V bar is there. It indicates we are going to express the specific volume in terms of molar specific volume, that is 1 multiplied by the molecular weight of the gas. Okay. So once you know this one, we have to find out the whatever the value of P. Okay, so that's why I'm telling you have to remember this equation. PV equals to MRT for ideal gas equation. and P plus A by V square into V minus B equals to R bar. You see, P plus A by V bar square into V bar minus B equals to R bar T, where V bar is molar specific volume. Okay, suppose if you are putting 1, it is wrong. You have to put the volume in terms of meter cube per kg mole. That is P equals to R bar T divided by V bar minus B minus A by V square. Okay, so you have to convert to find out the value of T. So R bar T divided by V bar minus P minus A by V bar square. Okay, 8.31144. You remember R is 0.287 kilojoules per kg Kelvin, and R bar it is called as universal gas constant, and the value of universal gas constant is always 8.3114. Okay, so don't put 0.287 here. Suppose if you put 0.8287, it is wrong. So be careful in substitution of the values. R bar T divided by V bar minus B minus A by V bar square. So R bar is 8.3144 into temperature, and don't put the temperature in degree Celsius. Okay, you have to convert degree Celsius into Kelvin. Okay, so 100 plus 273, it is 373 divided by V bar is 44 minus of B is 0.0428. Okay, minus 365.6 divided by 44 square. Okay, so you'll get the P as 70.36 kilopascal. After simplifying, we are getting the value of P as 70.36 kilopascal. Now we have to use the ideal gas equation. Okay, ideal gas. Suppose you are expressing in terms of kilogram, you can use PV equals to RT. Suppose if you are going to express in terms of molar, you can put like this also. PV bar equals to R bar T, where V bar is molar specific volume and R bar is molar gas constant, or it is universal gas constant. Okay, so you should be very careful in substitution of the units. So our aim is to find out P equals to R bar T divided by V bar. Okay, R bar is 8.3144 and temperature is 373 divided by 44. So we'll get the pressure as 70.48 kilopascal. You will see you have to compare the values. Whenever you treat the carbon dioxide gas as the ideal gas, we are getting the pressure as 70.48 kilopascal. And suppose you are treating the carbon dioxide gas as the real gas, we are finding out P as 70.36 kilopascal. So there will be deviation of 0.12 kilopascal compared to the real gas. Okay, so this is how to solve the problem. Okay, so here what you are doing, you should know the values. Universal gas constant is 8.3144, and A and B values you are going to find out from the chart, from the thermodynamics data handbook. That's why just you go through how to see the values of A and B. So for particular gas, we are having the different values of A and B. Those are called as van der Waals constants, A and B. Okay. Okay. Next, second problem. Determine the pressure exerted by carbon dioxide gas in a container of 1.5 meter cube capacity when it contains 5 kg of gas at 26 degrees Celsius by using ideal gas equation and van der Waals equation. Okay. You see, first we have to analyze the problem. Okay. Here in the previous problem, they have given the specific volume, that is meter cube per second. Okay. In this problem, they have given the volume. Okay. There is a difference between volume and specific volume. Specific volume is going to express in terms of meter cube per second. And here, sorry, meter cube per kg, and here volume is in terms of meter cube. Determine the pressure exerted by carbon dioxide gas in a container of 1.5 meter cube capacity when it contains 5 kg of gas at 26 degrees Celsius by using ideal gas equation and Van der Waals equation. The first and second problems look similar, but in the previous problem, specific volume is given, but in this problem, the volume and mass given separately. Volume is 1.5 meter cube and uh, uh, mass is 5 kg. Okay, the first we have to find out PV equals to MRT. Use the ideal gas equation. This is the formula PV equals to MRT. So P equals to MRT divided by V. Okay, and we know that R, general gas constant, is R bar divided by M. So M R bar T divided by V into M. So M is 5 kg into R bar is 8.3144 into 300 divided by 1.5 into 44. So M is 5 kg, R bar is 8.3144, and temperature, as I said, you have to express in terms of Kelvin. Suppose if you are putting degrees Celsius, it will be wrong. So be careful in substitution of the unit, even though you are knowing all the formula and things, but proper substitution is most important. Okay, only substitution is very important. This kind of problem carry 10 marks. Suppose if you make any mistake, you lose the mark. Hence, be careful in substitution of the units. So M is 5 kg. R bar is 8.3144. Okay, I am telling again, there is a difference between R and R bar. R is general gas constant, that is Cp minus Cv, that is 0.287 kilojoules per kg Kelvin. So whenever you are going to express in terms of mole constant, it is 8.3144 into temperature is 300 into 1.5 meter cube into 44. So after substitution, we get the value of P as 188.963 kilopascal. Okay. So this is ideal gas equation when you treat the carbon dioxide gas as ideal gas. Next, when you treat carbon dioxide gas as the real gas, in that case, you have to use the Van der Waals equation. This is the formula. Okay, as I said, you have to remember properly this formula. That is P plus A by V square into V bar minus B equals to R bar into T. Okay. So reduced form for pressure is given by R bar T divided by V bar minus B minus A divided by V bar square. Once again, as I said, you have to refer table C8. Okay, one more table is there, C7. That table C7 mainly used to find out the critical parameters. We studied critical parameters, reduce parameters, reduce volume, temperature, pressure, etc.
C6, the C6, no?
C6,
C6 is a critical parameter.
reduce parameters. Okay, okay, okay. Sorry, C6. Sorry. So correct, C6, that is. Okay, I thought of C7, but it is C6. Correct. Okay, to find out reduce temperature, reduce volume. Okay, you know how to see that table already.
Yes,
I'll
sir.
explain. Okay, I'll explain in the next problem. Okay, so now I am explaining how to see the table C8 to find out pressure by knowing the Van der Waals constant A and B, and all the units in the table are in kilo units. Okay, no need to remember this one. Okay, just you write down kilo units. That's it. From table C8 of page number 59, the Van der Waals constants are A equals to 365.6 and B is 0.0428. Okay. Now we have to find out, you see the difference between V and V bar. If V means only the meter cube per kg, V bar is meter cube per kg mole. Okay, V bar is whatever specific column is given, multiply by your uh, molecular weight. Okay, so here in this case specific volume is not given, but volume and mass are given separately. So molecular weight is 44 into volume is 1.5 divided by 5, so it is 13.2 meter cube per kg mole. Okay, specific volume is just 1.5 divided by 5. Okay, that is the specific volume. That is meter cube per kg. When you are going to find out V bar, you have to multiply by molecular weight of carbon dioxide. You remember the molecular weight of carbon is 12. The molecular weight of O2 is 16 into 2, 32. Molecular weight of nitrogen is 14. The molecular weight of hydrogen is 1. Okay, these are the 5 gases you should remember. Okay, next, uh, we had to find out the pressure P. Okay, now what problem I'm discussing, same kind of the problem we'll get in the main exam as well as for this one internal exam. That's why try to understand the problem carefully and just to go through how to see the tables properly. Okay, so we have to substitute the value P equals to R bar. R bar is 8.3144 and don't put 0.287. I'm telling you, suppose you put 0.87, it is wrong. Okay, so be careful. It is universal gas constant. So we are studying the general gas constant in case of ideal gas and universal gas constant in case of real gas and ideal gas mixtures. Okay, and temperature also don't put in degrees Celsius. You have to always put it in the Kelvin. So divided by V bar is 13.2 minus B is 0.0428. Okay, minus 365.6 divided by 13.2 whole square. So we'll get the pressure as 187.48. You see, just you have to compare. Okay, so by treating carbon dioxide gas as ideal gas, we are getting P as 188.963, and by treating the carbon dioxide gas as a real gas, we'll consider 187.480. Okay, and as I said, real gases are the gases which gives the deviation from ideal gas. We are having a factor called as compressibility factor. PV equals to ZRT. You remember, Z is called as the compressibility factor, and the value of Z is exactly 1 for ideal gas, and the value of Z is less than 1, or it may be greater than 1 for real gas. Okay, PV equals to ZRT. If Z is exactly 1, it indicates it is an ideal gas. If Z is less than 1 or it is greater than 1, we are calling it as a real gas. Okay, remember Z is PV by RT. It is the deviation factor, so which deviates from ideal gas. Okay, this is Z compressibility factor. Okay, now third problem most is the most important problem. So using compressibility chart. Okay, I shared the compressibility chart also. Just you go through. Okay, third problem. Okay, same kind of the problem they may ask, but they can change the gas. Okay, instead of carbon dioxide gas, they may give nitrogen oxide, nitrogen or hydrogen, like that. Okay, according to the gas, you have to find out the chart. Okay, now I'll explain how to see the compressibility chart. Determine the specific volume of carbon dioxide gas at 200 degrees Celsius pressure and at temperature and 60 bar pressure by using perfect gas equation and compressibility chart. Okay. So in the previous problems, we use the chart C8, but in this problem, so we are going to use the compressibility chart. So determine the specific volume. Our aim is to find out the volume of the carbon dioxide gas by perfect gas equation, means treating the carbon dioxide gas as ideal gas, and second case the carbon dioxide gas as the real gases. Okay, by using compressibility chart. Okay, the perfect gas equation or ideal gas equation already you know. PV equals to MRT. So V equals to MRT divided by P. M is mass of the gas, and R, whatever R is there, that is R bar divided by M. R bar is universal gas constant divided by molecular weight of the gas. Okay, into T. T is temperature. Temperature is given as 200 degrees Celsius. You have to convert Celsius into Kelvin divided by pressure. Okay, M is 1 kg. Suppose they are not given anything, it means that it is 1 kg only. Specific volume means it is per kg only. Obviously, M is 1 kg. R bar is 8.3144. into temperature. Temperature is 473 Kelvin. We studied the relationship between temperature scale in module 1. Okay, so we are having various temperature scales like a Kelvin scale, Celsius scale, Rankine scale, Fahrenheit scale, etc. So we established relationship with also. Okay, whatever problems are discussed in the module 1, those are also most important. Okay, so you should remember the relationship between a Celsius scale and Kelvin scale. You have to add 273. That gives the temperature in Kelvin scale. Okay, and divide by molecular weight of carbon dioxide gas is 12 plus 32. You'll get 44. And one more thing here, pressure. You should be very careful in substituting the pressure value. Pressure is given 60 bar. Okay, all the values are in kilo units. So you have to convert 60 bar into kilopascal. How we are going to do? Okay, 60 into 10 to the power of 5. So this is Newton per meter square. In order to find out kilo divided by 1000, I am telling you, suppose you put 60, no, it will be entirely wrong. That's why converting the 60 bar pressure into 60 kilopascal is most important. How we are going to convert 60 into 10 to the power of 5 divided by 1000? Okay, so you'll get around 3 gets cancelled. 60 into 100 means 6000 kilopascal. You get it. Okay. So after substituting the value, we are getting the specific volume of carbon dioxide gas as 0.01489 meter cube per kg. Okay. Next important table means it is C6 from page number 58. Okay. uh, we have to find out the critical parameters. Okay, we studied the critical parameters. Anybody, what is the relationship between critical parameters and reduced parameters? Do you know what is critical pressure? What is critical parameter? We derived van der Waal equation in terms of reduced parameters and critical parameters. Okay, so reduced parameters, we are defining it as the actual parameter divided by critical parameters. Critical parameter means, for example, critical pressure is the pressure of the working substance at a critical point. Okay, critical, like that we are having a critical temperature and critical pressure, etc. So you should remember, okay, reduced parameter is actual parameter divided by critical parameters. So to find out critical parameter, you have to refer the table C6. Okay, there will get I think in the right columns, right, 3 to 4 columns are there. For particular gas, we are finding out the critical temperature, critical pressure, critical density, etc. Okay, so go to the carbon dioxide gas row, write the values of a critical temperature. Critical temperature is 31 degrees Celsius. Critical pressure is 73.85 bar. Critical density is 460 kg per meter cube. So first we have to find, because as I said, the compressibility chart. Okay, before that I'll explain what do you mean by compressibility chart. Okay, so what you are seeing on that screen is, it is called as compressibility chart. Okay, so compressibility chart, we should know minimum two values. Okay, compressibility chart, in the y-axis we are having compressibility factor Z. It's the deviation of real gas from ideal gas. In the x-axis we are having the reduced pressure. Okay, and so what curves you are finding out, these are called as reduced temperature curve. Okay, so hence it is very necessary to know the values of TR, that is reduced temperature and reduced pressure. So once you know these two values, then only we can find out the value of Z. So without knowing this one, you are not going to find out the critical compressibility factor Z. Okay, so whatever the curves you see, so this is the deviation at reduced temperature of 1, and it is 1.2, 1.5 and 2. Okay, so you get all the values in the compressibility chart. Okay, so analyze that compressibility chart carefully. So this is the nature of compressibility chart. It is a one of the important tool or instrument used in the real gas behavior to know the compressibility factor. Okay, so you are knowing the actual parameters, okay, and critical parameters you are going to obtain from the chart C6. Okay, by knowing these two values we can find out the reduced pressure and reduced temperature. As I said, the compressibility factor, it is a function of pressure and temperature. Okay, you studied law of corresponding states also. Okay, it's mainly the function of temperature and pressure. That's why we have to know the value of PR and PR. So PR and PR, by knowing these two values, we can find out the remaining things. Okay. So, reduced pressure. How to find out the reduced pressure? As I said, the reduced parameter, it is the ratio of actual parameter divided by critical parameter. The actual parameter is given in the problem as 60 bar pressure, and from the chart corresponding to carbon dioxide gas, we'll get the critical pressure as 73.85 bar. Okay, those what value you are getting is the most important value, that is 0.812, that we are going to search from the compressibility chart. Like that, how you are finding out? You have to find out the reduced temperature also. Reduced temperature is given by, it is a ratio of actual temperature divided by the critical temperature. The actual temperature is, once again, as I said, you have to find out in terms of Kelvin. Okay, so don't go for your mm, degree Celsius, so you'll get the different values. Okay, better you have to put it in Kelvin temperature. 200 given value, and 31 what you are obtaining from the table of C6. You'll get the TR as 1.555. Okay, as I'm telling, so you'll not get 1.555 values on the table. You have to search for the nearest value. It is nearly equals to 1.6. Okay, corresponding to pressure of 0.812. You see, you have to take the vertical line and TR as 1.55. Okay, so zero point 0.8 and 1.6. You see, in the uh, compressibility chart. Okay, so zero point 0.1. Okay, you are having 0 0.2, 0 0.4, 0.6, 0.8, like that. So our reduced pressure is zero point 0.8. Okay, and TR, you see, we are having 1.2, 1.5. Okay, in the actual compressibility chart you'll get 1.6 also. So what you are going to do? So first you move vertically up where it crosses, where it touch the 1.6 TR line. Okay, so there you mark it. Okay, so location is most important. So you have to move vertically. Suppose you are getting the critical pressure, reduced pressure as 1 bar, directly you can refer this one. But in what value we got, it is 0.8. 0.8 is nearest to this one value. But in actual compressibility chart, you'll get all the values, zero point 0.8 and 1.6. So will come this one. Okay, and then first you locate the intersection point corresponding to PR 0.81 and reduced temperature as 1.6. So then you move in the left direction, okay, on the y-axis. You will get approximately 0.95 or 0.96. I'm telling you it is approximate value. So little bit variation will be there. Don't worry about that one, but you try to get the values. Okay, it's not accurate. So according to how you are going to see, it depends upon that one. But you can put the nearest value around 0.95, 0.96, 0.97. You'll get, okay. As per my knowledge, you'll get 0.96, I think. Yes, you are getting the value of Z as 0.96. So go to compressibility chart, search the value of PR and TR. You'll get the value of compressibility factor as 0.96. Okay. Now our aim is to find out the volume. So volume is Z equals to PV by RT. Okay. So we know all the values except we. I'm telling you PV equals to RT for your ideal gas equation. PV equals to ZRT for your real gas equation. Z equals to PV by RT. So V equals to ZRT divided by T. Okay. So V equals to Z is 0.96. As I'm telling you, Z is exactly one in case of ideal gas. In case of real gas, we are obtaining it as 0.96. I'm telling you it is approximate value. Some of you may get 0.95, some of you may get 0.94. Whatever value you are getting, just you put that value, and then you have to mention clearly which table you are referring. Okay, from the compressibility chart corresponding to pressure of zero point 0.8 bar and reduced temperature of 1.6, we are obtaining the compressibility factor as 0.96. You have to mention clearly in the answer script. Okay, into R is, as I said, it is R bar divided by M, that is 8.3144 divided by 44. It is your molecular weight into 200 plus 273 uh, divided by, you see, P, you should be very careful. As I said, all the units are in kilo. You have to convert in kilopascal. 60 bar, first you have to convert in pascal. So 1 bar equals to 10 to the power of 5 pascal. Then how to find out kilopascal? Divided by 1000. You will get, after substituting the value, you will get the volume as 0.0173 meter cube per kg. Now, after getting the value, you have to compare. Okay, so using ideal gas equation, how much you are getting? 0.01489 and 0.0173. So this much of the deviation will get while treating the carbon dioxide gas as the real gas. Okay, so whatever the problems I solved, this kind of the problem only you may get in the exam. Okay, now, okay, I'll do another problem. Is related to the oxygen gas. Determine the critical pressure of oxygen gas using perfect gas equation and also the van der Waals equation. Okay, so we have to find out critical pressure. Okay, in the previous problem we found out the pressure of the gas, volume of the gas. In this problem we have to find out the critical pressure. Okay, critical pressure means the pressure of gas at the critical point. Okay, now they are given VC. VC is critical volume is given, and critical temperature also given in the problem. Suppose if they are not given, you can find out from the table C6. But in this problem, they are given all the values. Okay. Now from the perfect gas equation, you can use PCVC bar equals to M R bar TC. C indicates the critical point. How you are using just PV equals to MRT, just use suffix it as C. C indicates critical point. Okay, you studied one more point called as triple point in pure substance chapter. So critical triple point is the point where all the three phases like solid, liquid, and vapor states coexist in equilibrium condition, and the triple point of water is 0.01 degrees Celsius. You remember sometimes they may ask what is the value of a triple point of water. Okay, the triple point of water is 0.01 degrees Celsius. PCVC bar equals to MR bar TC. So PC equals to MR bar TC divided by VC bar. Okay. M is mass of the gas. Anyhow, specific volume indicates per kg only. M is 1 kg into R bar is 8.3144. Okay. You see, R bar, you have to take the universal gas constant. Temperature, critical temperature is given in the problem as minus 118.10 plus 273. You have to put it in Kelvin. Divided by VC is given in the problem 0.0745. So they are given the values. Otherwise, you can find out from the chart. Now we are getting the PC as 172.87 bar. So what we are finding out this value by treating the oxygen gas as the ideal gas. Now we have to find out what is the critical pressure using the real gas equation. As I said, there are so many real gas equation, but van der Waals equation is the one which is most widely used. That's why you have to remember that equation only. Okay, and we derived the expression. Okay, R bar is 8 by 3 into PC VC bar divided by TC. Okay, while deriving the equation, we derived this one also. You remember Uh, in terms of critical parameters, the gas constant is given by this formula. So you have to remember this formula to find out any critical parameter. It may be PC, or it may be VC, or it may be TC. So whatever equation is there, this is the equation which gives the relationship between the universal gas constant and critical parameters of the real gas. So R bar equals to 8 by 3 into PC VC bar divided by TC. So PC equals to 3 by 8 into, so from this one only we can find out the PC as 3 by 8 into R bar TC divided by VC bar. Okay. 3 by 8, okay, into R bar is 8.3114, and TC is given in the problem minus 118 plus 273 divided by 0.6745. So after solving this one, we are getting the PC as 6482.72 kilonewton per meter square. Okay, and then we have to convert in bar. Okay, so we have to convert like this. 64.82 bar. You see, uh, you have to compare the two values. Okay, by treating the oxygen gas as the ideal gas, we are getting the critical pressure as 172.87 bar, and by treating the oxygen gas as the real gas, we are getting the value of PC as 64.82 bar. Okay, this much of deviation you see, around how much, three times, nearly three times greater in case of ideal gas, and in case of the real gas we're getting approximately 65 bar. Okay, this is how to find out using the chart. Okay, next problem is related to the nitrogen gas. You see problem number 6. For nitrogen gas, determine the compressibility factor Z. Okay, at 10 bar pressure and minus 85 degrees Celsius, and they are given the two condition. Okay, our aim is to find out the compressibility factor of nitrogen gas at two condition. One is condition is at 10 bar and minus 85 degrees Celsius, and another condition is at 5 bar and 35 degrees Celsius. Okay, now, once again, you have to refer table C6 of page number 58 from the thermodynamics data handbook, and you see what kind of gas is given. The nitrogen gas is given. So there are so many rows in the chart: nitrogen gas, oxygen gas, carbon dioxide gas. So many gases are there. So whatever gas is given, just you go through that one. Nitrogen gas corresponding to the nitrogen gas from table 6 of page number 58, we are getting the critical parameters. Critical temperature as minus 147.1 degrees Celsius plus 273. We get 125.9 Kelvin. Then PCR is 33.94 bar, and rho CR. Okay, rho CR. Okay, anyhow, we are not using this one, rho CR, but meantime, you can write that value also. 310.96 kg per meter cube. So density is the ratio of mass to volume. Unit is kg per meter cube. Anyhow, we are not using this rho anywhere in the uh, problem. And uh, now use the existing equation. PR, reduced pressure, is actual pressure divided by critical pressure. Okay, actual pressure is given 10 bar, first condition, divided by critical pressure is 33.94. You are getting the reduced pressure as 0.2946. Similarly, reduced temperature as the actual temperature divided by a critical temperature. Actual temperature is minus 85 plus 273 divided by 125.9. So we are getting TRS 1.5. Okay. And once again, by knowing the critical pressure and reduced temperature and reduced pressure, you refer the compressibility. You remember this kind of value will not get in the compressibility chart. So just you go through the nearest value. Nearest value is 0.3, and here TR is 1.45 is nothing but 1.5 only you can take. Okay, because this value will not get in the compressibility chart. Corresponding pressure of uh, zero point 0.3 and TR as 1.5, we are obtaining the compressibility factor as 0.98. Okay, in that range only you'll get 0.95, 0.96, 0.97, 0.98 up to 0.99. Okay, and suppose you're getting 1, it is wrong. So 1 indicates the ideal gas. You will not get a 1 value in the real gas. So be careful in finding out the value of Z. So it is usually 0.95 to 0.98. Okay, corresponding to pressure of 0.3 and TR as 1.5. From the compressibility chart, we are obtaining the Z as 0.98. Okay, this is the first condition. Similarly, you have to find out for second condition also at 5 bar pressure and 35 degrees Celsius. We have to find out reduced pressure is the actual pressure divided by your critical pressure. The actual pressure is 5 bar, second condition, and critical pressure from the chart, it is 33.94. You are getting 0.147, and TR, the reduced temperature as actual temperature divided by critical temperature. Actual temperature for second condition is 35 plus 273 divided by the critical temperature is 125.9. Be careful. So you have to express in Kelvin. You'll get 2.44. So corresponding to reduced pressure of 0.14. Anyhow, you'll not get 0.147. So search for nearest value. It means you'll get 0.15. Okay. 0.15 and 2.44. You'll not get 2.44. You'll get 2.4. Okay. So corresponding to 0.15 pressure and 2.4 reduced temperature. From the compressibility chart, okay, first you move vertically, locate the point, and then move horizontally from right to left. So you'll get the value of Z in the y-axis. So corresponding to PR 0.147 and TR 2.44, you'll get the value of Z as 0.9. You see, you are getting the value less than 1, then only it will be a real gas. Suppose you are getting 1, even though you are getting 0.998, you have to put that value only 0.998 up to 0.999. Okay, but when you are getting Z as 1, it indicates it is the ideal gas. Okay, any doubts, students? Okay, any doubts? Do you have any doubts in real gas?
No, sir.
Good. Okay, so in the real gas, concentrate on the van der Waals equation derivation. Okay, that derivation is most important. How to find out? Okay, there is a very big derivation. Try to practice yourself. Okay, you take one white sheet. Okay, try to practice that van der Waals equation. Okay, practice is most important. Without seeing and without reading, you will not understand. Better you take white sheet and you have to practice that van der Waals equation, then concentrate on limitation of van der Waals equation, compressibility factor, then reduce parameters, etc. Okay, and this chapter is simple. Okay, as compared to the other chapter, it's not so complicated. Okay, so concentrate on this one. So there will be chances of getting 20 out of 20 in this chapter. Okay, so and this chapter also not complicated. You have to remember only two formula. One is your ideal gas equation, and second one is your real gas equation, and also third formula is the reduced parameters is actual parameters divided by critical parameters, and how to see the compressibility chart and um, van der Waals equation chart. Hope you understood all the concept. All of you have to enter your USN in the chat box, please. Okay, without fail, those who have attended. Okay, so all of you have to enter. Now you enter. Those who are not entered USN, please enter. Okay. Okay. Thank you guys for joining the session. I'll stop the session now. Okay.